So today's lesson is going to be on the VSEPR theory, which stands for the valence shell electron pair repulsion theory. And this is a theory of how different atoms combine to form 3D molecular structures. And remember, a molecular structure is something that is a covalent compound. So we're looking at covalent compounds here. So you're going to want to pull out your chart from the website, and let's fill this in, and then we'll get some practice. All right, so what about our electron pair geometry? What if it is A2, meaning it has one bonding pair, and these are going to be things like our diatomic elements. For example, bromine, Br2, there's two bromines. It has one bonding pair. We would say that its shape is linear, and you can see that this is in fact linear. It has a bond angle of 180 degrees. And if we were to draw our structure on paper, it would look something like this, where the A is whatever element we're talking about, Br-Br, for example, if we were looking at bromine. We can replace one of the A's with an X, or we can do AX2. So now I have two different elements here. All right, A and then something else. All right, so here's my AX, or I could have another white piece coming off of the central atom, and that'd be like an AX2. It has either one bonding pair or two bonding pairs, BP4 bonding pair, and it is linear. All right, so for example, if we were to let me just put these together real quick so we can do a quick example here of AX2. So here's my A, and here's my two X's. All right, and I have two bonding pairs, but it is linear. All right, so that's going to give it a 180-degree angle. And if I was to ask you to draw it on your paper, you have A, or A is the central atom where the X's are on the outside. All right, and again, the A and the X are just representing whatever elements we're using from the periodic table. What if I have three things surrounding my central atom? So in this case, I might have three bonding pairs, and that is going to be trigonal planar. With a bond angle of 120 degrees. And we would simply draw it on our paper if I ask you to, something like this. All right, and this is going to be a trigonal planar. Notice I do have a 120-degree angle here. I have my central atom, which is the A. I have my X, which is the white in this case. And so it is a trigonal planar. Now, what if I take off one of these X's? So I take off one of these X's. What am I left with? I am now left with three things around the central atom. Two of them are bonding pairs, and this is a lone pair. So I have two bonding pairs and one lone pair, LP for lone pair. We would call this a bent structure, and its bond angle is going to be less than 120 degrees. That is because this lone pair of electrons pushes down our two elements. So we know that these elements, theoretically, they have the, in the center, they have the protons, and surrounding the protons are the energy levels with the electrons. So this lone pair is just electrons, so it's more, there's no protons really essentially there. We've got just the electrons, and we know that we have electrons here, and we have electrons here, and like charges repel, so these are pushing the electrons away. So if I ask you to draw it, you would just simply be able, you could simply draw it AX with our lone pairs. All right, what if I have four things around the central atom? That would be AX4. All right, and it's going to look something like this. Here's my AX4. All right, so my black piece of the model is the A, and the white are the 4x4s, okay, the 4 X's. Now, I have 1, 2, 3, 4 bonds, 4 bonding pairs. If it has 4 bonding pairs, we say that it is tetrahedral. And we are going to have a bond angle of 109.5 degrees. And we would draw it with A in the center, and our elements represented by X surrounding the central atom, which is the A. Now, what if I remove a bonding pair? I remove a bonding pair. I still have 4 things around the central atom. But in this case, I now have 1, 2, 3 bonding pairs, and then this lone pair. So this lone pair is going to do the same thing we saw in the previous problem. It's going to take and push these X's closer together. So when I have 3 bonding pairs and 1 lone pair, my bond angle is less than 109.5, and we would call that molecular structure trigonal pyramidal. And if I ask you to draw this on your paper, you're going to just put your X's surrounding that central atom and your lone pair. What if I remove another lone pair? I'm sorry, I said a lone pair. I have removed another, so let me start over here. What if I remove a bonding pair? Excuse me. I remove a bonding pair. So now what do I have? I have 2 bonding pairs, and I have 2 pairs of lone pairs. So 2 lone pairs and 2 bonding pairs. These lone pairs are going to push and take our X's and push them even closer together. So when I have 2 bonding pairs and 1 lone pair, we say that this structure is also bent, and it again is less than 109.5 degrees. Now, for the purposes of our class, you don't need to know the actual angles. Trigonal pyramidal is in fact 107, and bent is going to be 104.5, so bent is a little less than the trigonal pyramidal, but for our class, less than 109.5 is appropriate. And again, if I ask you to draw this on your paper, you're going to put the central atom A, surround it by 2 of the 2 X's, and then you're going to add in your lone pair. So let's do some examples with this now that we have this chart. Now, you will not have this chart on your assessment, so you need to learn it. Now, a bonding pair can be a single bond, a triple bond, a double bond. It does not matter. All right, so here's the example that I like to use. If a female is pregnant and she has one child during her pregnancy, how many times was she pregnant? She gave birth to one kid. She was pregnant one time. Now, what if she had twins? She has two babies, but how many times was she pregnant with that one set of twins? And that's once. It was still one pregnancy. All right, so that's a double bond. A triple bond would be like if a female had triplets. She has three babies, but she still had only a single pregnancy to carry those three babies to term. All right, so it is a triple bond. So a bonding pair can be a single, a double, or a triple bond. All right, and here's an example of what something with a double bond would look like. All right, it's got two bonds, 1, 2, but it is still considered a bonding pair. Notice, all right, there is one atom and one atom. All right, so there's still a bonding pair. It just so happens to be a double bond. So let's go and let's do some examples. And we're now going to be on our Lewis structure worksheet from our website. All right, we know that valence electrons are the electrons involved in bonding. So step one, we have to figure out how many total valence electrons there are for H2. Each hydrogen has one valence electron. So I have two hydrogens. That means I have two total valence electrons. So when we draw our structure, a line represents two electrons. And in this hydrogen, I can only do two electrons. I have two here. And so this is an appropriate structure. Now, for some rules for drawing our structures, hydrogen can only have two electrons. Everything else is going to want 8 for the most part. Now, there are some things that can go above 8, and that is something that we would learn when you came to see me, if you came to see Chemistry 2. We would go into some exceptions to this. So for the purposes of our class, we're going to do 8 electrons. And then one additional exception, group 3A does what we call an incomplete octet. Group 3A only needs 6 electrons. All right, so that would be things like boron. Boron would only need 6 electrons. So how many bonding pairs do I have in the center? I have 1. So we would say that that is going to be a linear shape. Now, we're going to come back and talk about the polar, nonpolar, and the dipoles in a separate video. Let's just practice drawing for today's lesson. F2. Fluorine has 7 valence electrons. There are 2 fluorines, so I have a total of 14 valence electrons. My structure can have no more and no less than 14. 14 is the magic number. So I'm going to draw in my first lone pair, and then what I'm going to do is I'm going to come back around and I'm going to add lone pairs until I get to 14. So 2, 4, 6, 8, 10, 12, 14. That's my magic number. I'm going to check, do I have my octet rule fulfilled? This fluorine has 2, 4, 6, 8. This fluorine has 2, 4, 6, 8. So each fluorine does have 8. I have one bonding pair, So again, my structure here is linear. All right, let's draw oxygen. Now, oxygen, I'm going to draw in a pencil. When you draw Lewis structures, you really want to use a pencil because it requires erasing sometimes. Oxygen has 6 valence electrons, and there are 2 oxygens, so that is a total of 12 valence electrons. So I'm going to start off by drawing my bonding pair. And I'm going to go back and I'm going to add lone pairs until I get to 12. So I've got 2 already, 4, 6, 8, 10, 12. We add lone pairs, now we stop. Now let's check our octet rules. My oxygen on the right has 2, 4, 6, 8. But my oxygen on the left has 2, 4, 6. We need 8. So in this case, we are going to have to erase a lone pair and move it to part of the bond. So we now have a double bond. So we start with a single bond, and if we cannot fulfill the octet rule with the single bond, we then make a double bond. Notice I erased the lone pair first, and then I drew the bond. You need to erase the lone pair first, because what students do is students just put in a double bond here, but they don't erase the lone pair, and then they have too many. For example, let me put that lone pair I erased back. How many electrons do I now have? 2, 4, 6, 8, 10, 12, 14. I can only have 12. Also, what have I done? I've given this oxygen 2, 4, 6, 8, 10, and it can only have 8. So we have to erase our lone pair before we make a double bond. I still have only one bond here in the center, so this is linear. All right, and an example, let me show y'all what oxygen would look like using our model here. Let me rearrange some of these things that I have. All right, here's my oxygen. My double bond, 1, 2. Now notice each one of these oxygens has 2 lone pairs. All right, so in this particular example that I've got, notice I also have 2 lone pairs on each of my oxygens. All right, let's look at H2O. Hydrogen has 1 valence electron, and there are 2 of them, plus my oxygen, and oxygen has 6 valence electrons. All right, so this is going to be a total of 8. Now, hydrogen will always go on the outside because hydrogen can only have 2 electrons. I cannot put hydrogen in the center. When I put hydrogen in the center, I've given it 4 electrons. And hydrogen can only have 2. That was a rule. So I'm going to put oxygen in the center, and hydrogen goes on the outside. Now, I've got my lone pairs. I need 8, my bonding pairs. I need 8 total electrons. So I've got 2, 4. Now I'm going to go in and add my lone pairs, 6, 8. 8's my magic number. Let me check my work. This hydrogen does only have 2 electrons. This hydrogen also has only 2 electrons. And this oxygen has 2, 4, 6, 8 electrons. So it is happy. I have 2 bonding pairs and 2 lone pairs. So 2 bonding pairs and 2 lone pairs. Oh my gosh, I've got a typo here. That should say 2 lone pairs. So two bonding pairs and two lone pairs has a shape that is bent. All right, let's look at carbon dioxide. Carbon has 4 valence electrons, and oxygen again has 6. There's 1 carbon with 4. Oxygen is 6. There's 2 oxygens, so 6 times 2 is 12, plus 4, 16 total electrons. Carbon always goes in the center, so I'm going to put carbon in the center and my oxygens on the outside, 2, 4. Now I'm going to go around and add lone pairs until I get to 16. All right, 2, 4, 6, 8, 10, 12, 14, 16. Let's check our octet rule. My oxygen has 8, 2, 4, 6, 8, but my carbon only has 4, 2, 4. So I have to erase a lone pair, and then I can make a double bond. My carbon now has 2, 4, 6. It needs 8. So what am I going to do? I'm going to erase a lone pair, and I'm going to make a double bond. These electrons are being shared between the carbon and the oxygen. This is a shared. Remember, covalent electrons share electrons, or covalent compounds share electrons. So these electrons are being shared between the two atoms. The lone pairs go only to the atom which they surround. So this oxygen has these 2 lone pairs, but it is sharing an additional 4 electrons with carbon. Now, it is the central atom that is important when we are talking about our structure. Oxygen does have lone pairs, yes, but the lone pairs, because the oxygen is not in the center, do not affect the structure. Look at just the central atom. What do we notice about the central atom? It has 1, 2 bonding pairs. It has a bond here and a bond here. So 2 bonding pairs is going to give us a shape that is linear. All right. What about nitrogen? Nitrogen has 5 valence electrons. There are 2 nitrogens, so that's a total of 10. So here we go. 2, 4, 6, 8, 10. Now, it doesn't really matter where you put your lone pairs, all right? Let's look. This nitrogen has 2, 4, 6. And this nitrogen has 2, 4, 6. They both need 8. So what am I going to do? I am going to erase a lone pair. And again, it doesn't really matter which one you erase. But the nitrogen, this nitrogen now has 2, 4, 6, 8. But this nitrogen only has 2, 4, 6. So I'm going to erase another lone pair and make it a part of the bonding pair. So here we go. I now have 1, 2, 3, a triple bond. 2, 4, 6 total electrons. Nitrogen has the 6 being shared plus its lone pair, 8. And this nitrogen has the 6 being shared plus this lone pair for a total of 8. Now, the reality is when you draw these, you may have chosen to erase this side lone pair and left the lone pair up at the top. For the purposes of our class, I would be okay with that. It does really technically matter, but we're not going to get into the nitty-gritty details as to why the lone pair is on the nitrogen on the side here and not on the top. That would be a discussion for second level honors chemistry. All right, so for purposes of our class, I just need you to get the basic drawing structures down. I have a single bond in the center here. It's a triple bond, but it's a single bonding pair. All right, so 1 bonding pair would be linear. So what are we talking about? I've had a whole lot of discussion here about single bonds, double bonds, triple bonds. Let's just take a moment to define those. A single bond A single bond has 2 electrons. It is the longest bond, and it requires the least amount of energy to break. Okay. To break. All right, a double bond is 4 electrons. A triple bond is 6 electrons. It is the shortest of the 3 bonds, and it is going to require the most energy to break. All right, so we've done a lot of practice here. The remaining portion of your worksheet on the website has a lot more practice, and that is going to include more of our different shapes that we didn't necessarily draw in this video, like trigonal planar, tetrahedral, trigonal pyramidal. All right, so make sure you go and you do that worksheet and get some practice, because practice makes perfect.